Let's go ahead and get started with hashing. Hashing is going to lead into hash tables, which, by the way, a lot of programmers that I've talked to believe that hash tables are basically the, bless you, the data structure you should be using for essentially everything. I, of course, don't agree with that, but hash tables do have a lot of nice features that make them useful for many, many things. So, how many of y'all have seen the word hashing before? All right, where have you seen it?
When we used it in scripting.
In scripting, okay. What'd you do? Oh, you used hash tables there. Did you use it for anything else?
Not really.
Since it's a little plastic.
You've never talked about hashing yet? I thought you were in security.
Oh yeah. Oh yeah. I forgot about that. She's not completely on yet.
When what? Did y'all use
We
a?
haven't flipped the hallway switch yet.
Oh.
What?
Where is that switch located?
I don't know.
Oh.
I've been
It's
trying to figure
located
it out for
at
2
9
years.
a.m.
At 9 a.m. Oh, so it's not a
not
place
timer.
so much as a
It's
time?
a lot later than 9 a.m.
Oh.
Well, I thought you might be partially on by then. It's 12 p.m.
Okay.
It's like a subroutine.
You can only access it at 12 p.m. You're not going to.
We're just going to try and avoid talking about the subject. Got it. So other hashing, MD5, and then the SHA, 256, 512, et cetera, et cetera. These all have to do with hashing.
What is MD5? I've heard that.
That's to make they use it for making checksums. So it maps your file to a, 128-bit number?
You got it to 5.
Sure, to some bitness of number, but it always maps something, whatever it is, to a fixed size number. And that's actually the most important thing right now to understand about hashing, is that whatever you give in it, it's going to give you back a number between 0 and some bitness level. Does that make sense when I say bitness level, 128-bit number? No, not at all?
No,
Okay.
I'm fine with it.
That's me. It's a number. That's what I'm getting.
So if you have 8 bits,
Is that 1 byte?
yes,
Yes.
yes.
I'm working.
That's from 0 to 255 because 0 counts.
Yeah.
Or let me write it in a different way for you,
Why is it in 255?
because 0 counts. Because
So
0 is
where
one of
the
the numbers
numbers
in the
coming
range.
from? Yeah, where are those random numbers coming from? Is it a byte of bits?
Yes, it's in binary.
Yeah. All 1 is 255.
Because if you have 8 bits, 2, 3, 4, 5, 6, 7, 8. Y'all done this, right?
Yes.
Yeah, so
Been a while.
0, 2, 4, 8, 16, 32, 64, 1, 28. You add all that up, you get 255. I don't know why I put a 0 right there. I think I'm tired too. There we go. All right. So then, let's do 4 bits. What's 4 bits called? It's not a byte. It's a.
Half byte? That's what I was gonna say.
Oh, that's a good guess.
Is it bit?
It's a nibble.
Nibble?
Oh my gosh,
Ah.
yes. I thought 2 bits would be a nibble. That'd be funny.
No, 4 bits is a nibble.
What's 2 bits then?
Are you?
2 bits.
No.
No one cares about
I'm
the
disappointed.
crumb.
A crumb.
Yes.
A crumb.
I
So
wish.
0, 2.
I
No,
think
that'd be
that's
7
what
bits.
Ah. 31. I don't know.
Oh, close. Down one more.
30.
No, down another step of the logarithmic scale.
7 27s.
How about let's do this?
I can't
2 to the
read.
4th minus 1. What's that?
15.
Oh, wait.
15 now. I thought you were writing 28 the whole time. I was like, where'd you get 28?
Oh, no. Here you got 16 bits. That's 0 to
12.
2 to the 16th
Oh.
minus 1,
No.
which is, come on,
Ooh.
65,535.
Woo.
That's a lot of numbers.
I can't brain today.
So then 32 bits would be 0 to 2 to the 32nd minus 1. We'll just say some number over 4 billion. And then 64 bits. Hey, look, you found this pattern, right?
Yeah, I remember it now.
If anyone wants to try and calculate that, go right ahead. I think it has 19 digits. So the 128 would be
Let's do it.
even
I don't
larger.
want it, so.
Hmm?
Like, I could calculate that, but I don't want to.
So the idea of hashing is whatever you put into it, you're going to get a number. When I say the bitness, is whatever range. The bitness. I like to call it the bitness. I don't think that's actually the proper term.
Give 'em the
Instead of
fitness.
fitness.
It's the fitness of the bit.
But it makes more sense to me. Why? What's the technical term, Vito?
I don't know. She doesn't care.
So again,
It's
oh yeah, so in Perl, were they called hash tables? So other languages will call maps or dictionaries. Because,
Dictionaries. We learned that in Python.
yeah, Python, I guess Python uses, C# uses dictionaries, Java uses hash maps, and actually hash tables. They're all the same thing. So hash table, maps, and dictionaries are all going to mean the same thing. Because why use one word? We can use multiple ones. So the idea is that you're going to map a key to a value. So I guess in the picture we have so far, we have some input that we map to an integer, but it may make a little more sense if you have a social security number and you map it to a record for a person. So what type do we want? Well, we want a data structure that's very, 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 very fast, so close to 0.1 as possible. Why is 0.1 so nice?
Because it's the fastest.
Because it's the fastest. Inserts and deletes should be fast too. Objects in map have unique keys. All right. Key may have a single property. So when you use a map, at least the single map, not the multi-map, but the regular map, keep in mind that each key is going to be unique. Hey, let's go look at different ones real quick. So before y'all memorize that slide, let's go back to the
photograph.
perfect.
I wish.
Yeah.
Wow.
That would make school so much easier.
See, part of me wishes, part of me is glad I don't.
Yeah, because then you'd remember all those ugly things in life.
Yeah.
So we want to be able to insert.
Yes.
We want to be able to, we'll call it get. Now this is based on a key value, so you may insert, we'll say someone's number 1, 2, 3, 4, 5, blah, whatever. And it'll be a student called, what do you want the student's name to be?
Olaf.
Olaf.
Christmassy. Yeah.
And then if you do a get on Olaf, there we go, you're going to get 1, 2, 3, 4, 5, and then you can of course remove Olaf from existence. And that way, later on, if you called get on Olaf, you would get back error. All right, so that's what we want.
Would it return? Would it actually return an error? Or would not return some other value, like a -1 for false?
All right, we'll make it return -1. Sure, why not?
I'm just asking in case that's like a function we have to implement.
Oh, you will return the default value.
Okay.
So the
So-
number is the key value, right? In this case?
The key is the number, and the value is right now a string.
Okay.
Okay. So, what about arrays? Hey, we'll have unsorted,
It's sorted.
sorted arrays. There we go. Is this marker too light?
No.
Good.
It's on me.
I just take your line.
If you can call it.
So, if it's an unsorted and you want to add to an array, what's the big O? Ah, we got worst case. Okay, this marker
It
is good.
depends on where we're adding. Are we adding at a position?
Oh,
or
I
to
failed.
that
Good thing I didn't go in the NBA.
That's why nerds don't play basketball.
Yeah, some do.
They're not nerds, they're athletic people. You can't have both.
All right, what's the worst case here?
Now you can't. You have to be one or the other.
Let's say you have to put it, you try and put it at the end of the array, but the array's full, so you have to allocate a new array and copy everything over.
In log in square, something.
What do you have to do? Hold on, stop. Stop just guessing.
Log in, I get it.
Stop.
Participation.
Stop.
Wouldn't it just be end as you're iterating through?
Yes, why is that?
Wait, what?
He did say because you're iterating through.
Through,
Yeah.
and why are you iterating through everything?
Because if it's at the end, then you have to start from the beginning.
But then you have to copy it over as well.
You have to copy it over, because an array
Okay.
you can jump to the end with no problem, but if you have to allocate a new array, you have to copy everything over, that's all
But
that.
if you count it while you're doing that, then you know what position.
You don't have to count the position because it's an array, you know where the end is, you just jump to it.
If you're keeping track of the end,
Yes, but why wouldn't you?
because you're dumb and you just forget to.
Arrays have indexes. What do you mean?
What's the average in best case then?
Oh, one.
Yeah, O of what?
Because you already know where the end is, and you just slap it on.
Slap it on. Okay. Sort. You want to insert an assorted array. What's the big O of that?
O of n to find where it would go, basically.
Well, you can do a binary search to find out where it goes, so that's log of n. But then,
So is it in log in then?
well, once you find the position, what do you have to do with the rest of the array? Let's say it's in the middle.
Move it.
Yeah, move it, and that's an O of n operation. So it's O of n, whoops, not because
Right,
searching.
Because you'd have to find the position and then shuffle everything
Yeah,
over
you
one
got
step.
it. You got it. Not because, yeah, exactly. All right, so, well, that's not good. Unsorted array, how long does it take to find something in there?
O of
N.
n.
Yeah. How about an assorted array?
You would have to log in,
Yes, because
the binary search.
binary search. How about removing in an array?
Are we removing it at the back or are we finding the value?
Let's say you have to find it and then remove it.
Okay.
Oh, that's
So
O of n
in-
squared because you need to find
get to
it.
the
Well, you find it,
Find it,
that's
remove
O
it, then
of
shuffle.
In
You
log
find,
in.
well, hold on. Whoa, not in squared, you're adding. Because O of n to find it, right? And then you run a second algorithm to shuffle everything down. So it's O of n plus O of n, which is just O of n.
Right.
Oh.
Okay.
Because you're not nesting the for loops, you're running one for loop and then running another for loop afterwards.
Right. I'm bad at this.
How about you remove an assorted array? Well, log it in to find it, and then what's the big O to shuffle everything down?
O of n.
O of n. Alright, not looking too good, especially since we wanted O of 1. Alright, how about a linked list?
Better.
Is it?
So
It depends.
we want to add to the linked list, let's say it's unsorted. What's the big O?
O of n or O?
1.
1, because you just add it to the list. You don't have to shuffle anything or shift everything. It's actually the word, you're not shuffling things, you're shifting. How about to find something?
O of n, because you got to iterate through the entire list until you find it.
Worst
Yeah.
case in, best case 1.
It's over. Remove something?
Oh.
Well, you gotta find it, and finding it,
Yeah, it's still O of n because
yeah. Now
Even though you
notice that
don't-
this is remove for what we want, not remove the head, because if remove the head, it'd be O of 1, because you can just do your pointer manipulation, but since we have to find it first, it's O of n.
plan for the worst case.
Alright, so linked list so far is terrible.
Why? It looks better than the other ones.
Okay, sure, it's got, at least it got, 1 out of 3, and I guess that ain't bad. Let's do the binary search tree.
You mean, yes, 0 out of 5 stars compared to 1 out of 5 stars. That's good.
1 out of 3 stars, right?
Yeah.
So binary search, we want to insert something. What's the big O? Now with binary search tree, there's going to be a worst, average, and best. And the average and best are the same, and the worst are something different.
Oh, well, the average is n log n.
Why is it in log n?
That's what I remember from the lesson. No.
That's the worst case, right?
Okay, what's the worst case?
That's what I was asking. Is it in log n for the worst case?
No.
No.
Stop taking guesses and think about what has to be done. When you're inserting something in a binary search tree, how long does it take to find the place it needs to go?
Takes log in because it's having the amounts
Each
of
time to find where it needs to be
indexes
placed.
per
Correct.
iteration, yeah.
And then once it finds its location, what's the big O of adding it there?
1.
1. So it's log of n plus O of 1, which is just
Log of n.
log of n. But what's the worst case?
N.
N. Why?
It just seems like the logical answer.
Because it's not having it, it's basically a linked list. Probably.
Right. If the binary search tree turns into a linked list, you have to iterate through the entire binary search tree to get to the n in order to place it. All right. How about this get something? How long does it take to find something on the binary search tree?
Log in.
For
Best case.
and the average case as well.
Worst case is O of n because of the same reason as above.
Yeah.
You might have to iterate through basically all of it.
All right. Now to remove something.
Log n.
For
Best
an
and
average.
average.
oh, you found the pattern. What's the worst?
And
Yes, because you have to search the entire thing if it's a binary search tree. All right. I don't know why this is a 1. There we go. Huh. All right. What's the next one we did? Oh, the heap. Is a heap going to help us here?
no.
No. So we're just going to cut the heap out.
Yay.
So let's
Yeah,
see.
it doesn't exist. Shoot.
Did we do anything else yet? I don't think we have.
We have not.
No.
Last thing we did was the SCL stuff.
STL. All right, so this isn't good. We're going to find something better. So arrays, technically, if you use the index into an array as the number, as the index into the array, you can make it O of 1. It's possible. It would just take up a lot. But it's not very space efficient, and as I'll show you momentarily. Binary trees can be log of n, are space efficient, but they're not O of 1. And hash tables will be a generalization of an array that under some reasonable assumptions O of 1. Wow, okay. We'll get to hash tables in a moment. So let's take an approach. Let's say you have your social security numbers of all the people in the US and you want to map them to different, are we doing students or people? Yeah, people. So you got access to everyone's social security number. Congratulations.
Woo, good job, Holland.
I'm still here. So we can use an array that goes from 0 to 999,000. Actually, that's a million. 999,999. But if you think about it, the population in 2004 was only 294,000. Actually, now it's what, 320 million? Yeah, it's 320 million. Right, Holland? I don't know why we're doing this to you today, but we are.
Security.
Security. I'll start asking Amber instead. So, over 60% of the array is still unused, which is not a very efficient use of space. So, as the slides have told you, the hash table is a very useful data structure, in case you didn't know it already. Great. Let's talk about this conceptually. So, you have your table on the left. Hey, what does that look like?
That looks like an array.
A hash table?
The one on the left is not a hash table. It's
Okay.
an array, and it's pointing to.
Objects. Things.
Wow, you know it's labeled.
Buckets.
Buckets. Whew. All right, so your reaction makes me want to make the final. Draw a smiley face, turn it in for 100. Everything else is a 0. and then just make a very long exam after that, just to see if you read the first line?
No, you make it in the middle of the directions.
Oh, okay.
Oh yeah, that's a good one.
Yeah.
Because I read like the first one. Oh no, we read.
Okay.
8:30 a.m.
Joke's on you, I'm good at reading directions.
All right. So notice that certain buckets can have more than one object in them, and that's going to be very important in a moment. Oh, actually, let's look at this. Let's see. Let's get my handy dandy mouse pointer. So object 5, the key is 1. So notice that it's in the array indexed 1, pointing to a bucket that contains object 5. All right, everyone with me so far? Object 4 with key 2 is from 2, pointing over. With key 4 is in index 4, we're going to ignore him for now. Actually, no, let's not ignore him for now. But also key 28 is right here in index 4. Can anyone take a guess why?
Because it's related data, so it also points to that.
Well, why isn't object 2 in one of these other spots that are not filled yet, or maybe hanging out with object 5 in index 1? Why is it in index 4? It has a key of 28. Key of 28.
Is it looping somehow?
Yes. The hash tables, or the table size, sorry. The array size is 8. The key is 28. The table size is 8.
It's a multiple, I think.
You're on the right track.
So it's like 4 times 7, but why is it at?
And not 7, 8. The table size is 8.
Why is it at that specific location?
It's related data, so you store it together.
Does it matter it's in that it's in that specific?
Okay, so you're really on to relationships. So what's the relationship between 4 and 28? Because sure, there is a relationship.
I'm thinking the 4 thing over there is like a social number, and then the 2 objects, like one would be like first name and one would be last name, so you want to store them together instead of having them in 2 separate areas and then having to call both areas.
I did like that story.
No.
But it has nothing to do with the objects, it has everything to do with the key. Because when you call get, you're doing a get on the key.
But you're doing
Huh, that's
value.
backwards. Ignore what's on the board. That board is totally backwards, it lied to you.
I was going to ask
So
you
you
earlier,
wrote
but I
the
figured
board,
you
so
knew
therefore
you
you
did.
lied.
Is it?
I totally lied to y'all.
Oh.
Totally lied to y'all. Man, that's
I
such
was
a
like,
big
maybe
lie.
you can do it both ways, and I just don't know.
No, that's fine. Anyways, the key is what matters right now.
Are you going through the table twice? And then 7 times 4 is 28?
7 times, you mean 8 times 4.
Yeah, that's what I meant.
8 times 4 is what?
32.
7 times 4 is 28. Yeah, it's 32.
Sorry. Right, it's 32. So it's not 4. Let's try 3. What's 8 times
You
3?
do 3, and then you go up to 4.
Right, so what's 8 times 3?
24.
24. And then what's left over?
4.
4. How about, let's ask this question differently. What's 28 mod 8? Do y'all remember mod? Do
No, I don't.
you remember division? I mean, sorry. So mod, so you have regular division,
Remainder.
integer division.
Oh, the
Mod is the
remainder.
remainder.
Okay, I
So then
just-
28
Was I
mod
right?
8.
Was I right saying it looped?
Yes, in a way. I said you were all on the right track.
I couldn't hear that because someone else said,
Oh,
said something.
you were on the right track. Like I said, you're
4.
looping. So yeah, 28 mod 8 is 4. Hey, what's 15 mod 8? You can.
Yes?
7.
Yeah.
Yes.
Ah, there's a pattern.
You're the best at math.
We're so good at math. Actually, that's arithmetic. It's not math.
You don't get to agree with him.
I'm not.
Just shush.
All right, so a hash table solves these problems by using a much smaller array and mapping keys with what's called a hash function. So let the universe of keys used in the arrays of size m, a hash function h is a function of u to m that is blah, blah, blah. Wow, that's kind of confusing. Do they have a picture? So you have all these keys, and it's in the universe of keys, and they map them to numbers. Hey, look at that. So in this picture, key 2 maps to 2, key 1 and key 3 maps to 3, key 6 maps to 5, and key 4 maps to 7. How are we doing?
Why'd they name it key 4 but it matches to 7? I don't like that.
Well, 6 goes to
Because
5.
they're weird.
I'm sure the keys are all about your feelings right now.
They should name it key 7
Why?
because it goes to 7.
The numbers don't have to match.
I thought there was only one key for
I'd
each
rather
number,
be
but there's
gay.
multiple values that you can put for each key.
There is only one key for each value. Look back here. See? Object 3 has a key of 4, object 2 has a key of 28, but they're both mapping to 4 because you're modding it by 8. So they have different keys, they just have to be occupying the same location in the array.
This is different
It's
from what we
it's
got.
like if you put in the higher number, but it technically mods to 4.
Wait, what's different? I must know.
We only did one key to each number.
That's what this is doing.
No, like location-wise, we didn't learn that you put two in the same
Hold on. There's a
area.
big difference here.
Oh, the object.
Remember, the object is still different. It maps to this location. And once you get to this location, you have to search the bucket for the key.
Okay, we didn't do bucket thingy.
Yeah.
Well, right.
That's what we're confused about.
Yeah, so there's 2 steps here. In order to get something in a hash table, you gotta go to the index and then you gotta search the bucket. So it's not just, since they both map to 4, that just shrinks it down to a smaller bucket that you have to search.
Yeah, I
So-
only got confused with the sort of looping index it's doing. It just kind of took a, especially since I didn't hear what you said, it kind of took me a moment.
So how do you search for every key in that bucket then? Like making sure you get to the right bucket?
We'll get to that.
Okay.
So a hash value or hash index is used to index in the hash table. That's great. Why don't we go with an example? Oh, cool. So if you want to insert something, here's how you actually insert it. Well, almost. Let's say your key is an integer and your item type is called item. Sure. Then you run the hash function on a key, which gives you the hash value, and then you jump in that table and you set it equal to that item. All right. But we have to have a hash function, right? So let's see. First, let me fix this that no one stopped me for some reason.
Because we totally knew what you were talking about.
I know, I don't know what y'all are thinking.
Crazy.
So what's a hash function?
It translates whatever into some number in whatever range is the fitness of the hash.
So it doesn't do it automatically?
Do what automatically?
Like you actually have to write that?
Yes, you have to write the hash function. Although most libraries implement one for you.
Can we use
Yeah,
it?
because we didn't use one in Perl, I'm pretty sure.
Right, because Perl automatically does it for you.
Less. Does C++ do that? I'm guessing no, because we're having to learn it.
No, the STL will do it when you use the STL's map, but we're not going to do it in this lab, of course.
Ooh.
So why learn it that way?
Why learn what? The hashing?
No, I'm saying why learn the STL way since we have to do it the other way for the lab, so hard way.
Oh, no. Remember the point of this course. You learn each of your data structures by writing them yourself and then immediately throwing your code away and just use the library instead.
Yeah.
This sounds like math.
It sounds like math. Well, programming is math.
Because we would learn the hard way to do something and it's like, oh, here's a shortcut.
Appreciate the process.
I don't appreciate any
No, it's not the
process.
process you need to appreciate. You need to understand what's going on so when there's an error, it'll make sense to you. And you'll also know what is the best one to choose based on its performance because you've studied your data structures. What?
Name the class.
Okay. So if we have 1, 2, 3, 4, 5 and we're going to map it to a 32-bit number, okay, that's pretty easy. You just return the number, right? Let's say you want to int hash of a string. What can we do there? How can we convert the string to a number?
Isn't there like a conversion thing that you can just type in? Do you like Google?
Sure, but how are we going to do it ourselves?
You go through each. I don't remember how to do it.
Character?
Yeah.
And they assign to a number.
I'm thinking of Java. Just kidding.
Right, because they're ASCII values. Then what do you do?
Then you push the ASCII keys.
Where? What do we do with the ASCII keys? So I'll do for I equals 0 to str.length. This is pseudocode. All right. I'll say we return a hash. Here's my int hash.
Is the whole string just integers?
Yeah, the whole string is just characters,
But
but
I mean-
characters are just integers.
They
You
just
of
forgot
got
the
range.
semicolon.
Yeah.
Well, you know, when the compiler runs my whiteboard, I'm sure it'll tell me.
Yeah.
It's like, I read this code perfect.
So you could just go through each line then, like each character, and then fit it into.
What do we do with them? What do we do with them?
You assign to their ASCII values.
Well, no, you don't assign the ASCII values. All characters are already assigned an ASCII value.
Convert string character to number.
All right, then what do we do with that number?
Is that the key or not? No, that's not the key. Is it? I don't know.
Yes, but we got to do something with it. So we have a string of numbers.
You add it to hash.
All right, let's do that.
But where? I'm confusing myself.
All right, there we go. Yeah, that would work.
Does it actually, or are you just saying it works?
No, that works.
Oh, awesome.
Now, there's some issues with this in that different words are still going to map to the same number, which is not what you want in a hash function, but this at least jumbles it up somewhat. So another trick to do is have hash start at 1 and then multiply equal each one and let it really jumble around. Another thing you could do is take 3 of them, the first 3 characters, add them up, and then did the next 3 and the next 3. Once you have all those sets of 3, multiply them all together. There's different ways to do it. Well, that's one way to convert a string to an integer.
See, I thought, now this is not going to happen the way I thought it did, but I thought like whenever it converted to the ASCII, you could just add it like in sequence instead of having to add all the numbers up together.
What do you mean by add in sequence?
Like,
You mean concatenate the digits?
yeah,
Oh, you can concatenate the digits as well. That's also a trick.
and wouldn't that make it to where you don't get two, not letters, two words for the same key?
That would definitely help, yes.
Okay.
That would definitely help.
I'm confused on when we're putting the numbers.
Confused on which part?
Where are we putting the numbers?
Why are we putting the numbers?
No, where are we?
Oh, so we have this hash function. I called it hash. But over here, it's called a hash function. Let's say key was a string. This hash function would now return an integer that we could then do a table sub hash value and set the item in.
So this is the key.
This is converting the key into an integer.
Oh, okay. I just didn't understand.
The whole point of the hash function is takes whatever you have and convert it to an integer because you need an integer in order to index into a table.
I
So-
love when they do it for us.
Yeah, that's nicer.
We're going to have fun in architecture.
Lots of yelling.
Nothing's done for you in architecture.
Oh, no.
Nothing.
That's not
All right, that's not. Someone has to do that, okay, Emily? You have integer value strings, or you can have multi-part of different fields or multiple fields.
What's that?
Well, let's say you have a student class. They might have a name, an ID, street address, phone number. You can just take all those, combine them all some way to get a hash function at the end. So mod stands for modulo. Wow.
Modulo.
Modulo.
I like that word.
Like modulo, modulus, mod. Basically, we're all talking about the same thing. Modulo. Modulo. What? Go ahead. Oh, I thought you were going to correct me. No, not this time. All right, I'll mess up soon.
Just internal screening.
So remember, mod's the remainder. So 8 mod 5 is 3, because when you divide 8 by 5, the remainder is 3. 9 mod 5 is 4. 10 mod 5 is 0. 15 mod 5 is 0. 125 mod 5 is 0. Thus, for key values mod m, multiple of m gives the same result, 0. Wow.
And that's
Well-
how you find the bucket.
To put it in, yes. After you run the hash function, you mod it by the size of the array to know which bucket you're going to put it in. For example, if we hash keys, wow, look at all that. So we insert 2. 2 mod 5 is 2. 2 mod 21 is 1. Everyone got that? 2 mod 34 is 4. And then 54, where's 54 mod 5 is?
4.
And what's the problem we have?
There's already a key there.
Oh, it's already occupied. All right, what do we do?
Magic. That's when there's 2
Mm-hmm.
keys.
Mm-hmm.
Yeah.
Because right now we have an array, so we all understand how arrays work.
So then you make a bucket.
Yeah.
You make a
so-
bucket.
yeah,
What are we
so-
going to make the bucket out of?
10.
What?
Did it really sound like that?
What are we going to make the computer science bucket out of? What?
3D printer.
Technology.
Data structure. Binary tree. What?
A hash.
A hash. No, we've already done our hash.
I mean, I guess we have an array of arrays.
Yeah. That's you can do array.
We could do array, but
A
the
linked
idea is
list.
this bucket's small. So what?
A linked list.
Yeah, let's do a linked list.
Yeah.
There's something called a collision. They resolve to the same thing. We're going to talk about hashing with chaining, and chaining is where you have an array of a linked list. The other one's called open addressing, which we will talk about next class, which is more complicated, but is what everyone is usually what's used. So, but right now chaining is easier, in my opinion, to understand because a hash table, when you do hashing with chaining, is simply an array of linked lists. So you find which linked list in order to add the item, and then you put it into the linked list. All right. Problem is keys 34 and 54 hash to the same entry 4. We need to solve this by creating a chain. Hey, look at that chain. It's a linked list. That's the most interesting 12 in the world.
Yeah, that's what I was about to say. I was like, what's
Huh.
going on?
It's
Huh.
a new number.
It's the new 12. It's wouldn't that be the millennium? Because they're so lazy that it's fallen down or something? I don't know. Yep, that 12 just is not cool.
The old 12's now.
It partied a little too much.
Last night. Wait a minute. Why is the 2 here?
That's what I was like.
Man, that's wrong.
Story of my life.
All right, let's fix these slides right now.
Wait a minute. Why is
Fix
this
the
here?
12,
This is
fix
wrong.
the 2.
That's a 1. That's a 1.
Go ahead and
That's
fix that.
something.
Oh, no.
Oh, maybe you need to make the table
Oh.
bigger?
Oh.
Or is it multiple?
No, you see what happened? It went on the next line.
Huh.
So
Ah.
you put 2 and then 1.
I don't think that was me.
So
I totally stole these slides from I don't know who.
Your fault. You didn't fact check.
All right, there we go. 1 and 1. There, that makes way more sense, right?
yeah.
Good. What's the running time to insert, search, and delete? Ooh,
With a linked list?
no, in a hash table with chaining. So, we're going to go over here.
In squared?
We're going to call it the hash table with chaining. It's the HTC. All right, so we want to insert something. So we take the key. What's the first thing we do with the key?
We have to run the hash thing.
A hash thing, which is, we're going to say an O of 1 operation. And then what do we do with that?
Then we've got to mod
mod, and that's an O of
one.
1 operation. Then we have to jump to the array, which is a
One.
O of 1 operation, and then we have to add it to the linked list, which is a
Over one.
O of 1 operation. Huh. So
That
let's
was
insert
nice.
in the hash table with chaining.
Over one.
O of 1. Oh, that's great. All right, what if we need to get something? I probably shouldn't erase that because we have to run the hash function, which is O of 1. Then we want to run the modulus, which is O of 1. Then we need to jump to the index in the array, which is O of 1. Then we're in the linked list. Now we have to
O of n.
search the linked list. But is the linked list going to be the size of the hash table?
No.
Not sure
What
about
other
that.
variable can we use then? O of m?
So I'm going to call this worst, average, and best. Let's say in the worst case, everything mapped to the same location in the hash table. It was
Then
a
it's
really,
O of n.
then it's O of n. But on average, and in best case, everything's spread out evenly, which means the linked list has a size of 1. So then searching a linked list of a size of 1 is,
Okay.
O of one?
oh, right, O of n, where n
O of
equals 1.
one.
Yeah.
That's what I meant.
That's amazing.
All right, and then we have, how about removing? So worst case, everything mapped to the same location,
So O of n.
O of n, because we'd have to remove from the linked list.
Best is O of one.
Yep, average and best is going to be O of 1. Hey, look at that!
So beautiful.
So pretty.
So why don't you consider this the best, like all the other main programs?
Look at the worst case. Is O of n. Second, you have to do all this hashing function stuff, which may not actually work correctly.
Yeah, but if you look at an unsorted array, it has the same worst case. But that's its best case.
Yeah, we'll get to all that in a bit. So inserts O of 1, search is maximum, same as search, good. Therefore, in the unfortunate event that we have a bad hash function, all n keys may hash in the same entry of O of n runtime. Hey, when can that happen? So what's a good hashing function? We want something that has uniform hashing. Let's go to please give me a picture. Here we go. So a good one, let's say for example you have mod 7 and your keys are 5, 10, 15, 20, 25, 30, etc., etc., etc. And your mod 7, hey look, everything is equally distributed out within this hash table. Does that make sense? Because 5 mod 7 is 5, 15 mod 7 is 1, I skipped 10, 10 mod 7 is 3, 20 mod 7 is 6, 25 mod 7 is, what's that, 4? And so it jumps around evenly. But what would happen if they don't tell you what I was going to tell you? What if the array size was 5?
It would not be pretty.
Yep. Where would they all go?
0.
They would all go to 0.
That's not good.
That's not good. No bueno. So this hash table really does depend on your hashing function for its performance. Let's see, do we have anything else? Keys are non-random, usually parts of something, so you want to come folding and try and come up with a good distribution. Are we done with this? Good. So we're not going to do open addressing. We're going to stop now.
So is there like a standard for like the hashing function that like is generally better than most, or is it just based on like case by case thing?
Hold on. When you say hashing, what do you mean? The hashing function?
Yeah.
No.
Right.
I mean, you go look at security at the different hashing functions that are available. They run competitions about who's going to be the next standard, and then they pick whoever has the best one. And when you watch these hashing functions, they're just randomness, it seems, of what they're doing. And it just happens that this guy picked one that's fast and secure enough.